So there's this neat trick. It's called the 68, 95, 99, 7 rule. One nice thing about it, the name says it all. It helps you remember everything you need to know for it. So the name is admittedly a mouthful. 68, 95, 99, 7 rule. What does it say? It says that within one distribution of the mean, you'll find 68% of the observations of the data, if we have a random variable that is distributed in an approximately normal way. So if we have something that's unimodal and symmetric, that's usually enough for us to say 68% of the data will be within one standard deviation of the mean. 95% of the data will be within two standard deviations of the mean. So if we think about our bell curve going up, around that peak we have a yardstick. Remember, we use standard deviations as a yardstick. If we go one standard deviation out in either direction, we have 68% of the data in that main part of the hump. If we go out another standard deviation on each side, means now we've gotten down almost to the tails, and we have 95% of the data within two standard deviations of the mean. If we go out three standard deviations, we're definitely out in the tails now, and we have 99.7% of the data within that part of the distribution. So that means only 0.3% is outside. Those are on the tails, out beyond three standard deviations. That means, since it's symmetric, we could say roughly 0.15% is way off to the left and 0.15% is off to the right. So that's the 68, 95, 99, 7 rule. Now, why is it actually helpful? Well, it's helpful because that's all we need to get at least an approximation of a probability for how likely something is to occur when we're talking about something that follows a roughly normal distribution. So I talked about my drive time from Nashville to Bowling Green, and we looked at whether I take the downtown route or whether I take Briley Parkway. And Briley was a little bit longer. The average travel time was longer, but it had a smaller standard deviation. If I took the downtown route, it had a larger standard deviation because there's a chance that traffic would cause me to be backed up, even though on average it was a faster route. So if you'll recall, we used that when we first started talking about z-scores. So z-scores were saying how many standard deviations away from the mean, from average, are we? So we calculated that for me to be late, if I were taking the Briley Parkway route, it would have to be a 2 standard deviation day. We had a z-score of 2. If I were taking the downtown route, I only had to be 1 standard deviation above average when I started being late. Well, with the 68, 95, 99, 7 rule, we can actually say how often I should expect to be late if I'm traveling those routes. So if I start being late when I'm 1 standard deviation above average taking the downtown route with a z-score of 1, that means, well, whenever I'm average or faster to the left of average, I won't be late, obviously. So that's 50% of the time, right? Now with a symmetric distribution, we know that 68% of the data is within 1 standard deviation of average, but let's just look at what's above average up to 1 standard deviation. Since it's symmetric, we know that that's half of the 68, so 34% of the time. Those are the days that it'll take me longer than average to get there, but less than 1 standard deviation, so not really slowed down in traffic, just slowed down more than your average day, right? Well, 50% of the time I was fine because I was faster than average. 34% of the time I was slower than average, but still okay, still not late, still below that 1 standard deviation mark where I start being late. So that means 50% of the time plus 34% of the time. 84% of the time, if I take the downtown route, I'm going to make it to class on time. What does that mean? Well, 84% of the time I'm on time, 16% of the time, 100% minus the 84, 16% of the time I'm going to be late. That's when I'm more than 1 standard deviation above average when it comes to travel time, and that's when I'm late. 16% of the time taking my downtown route. What about if I take Briley? Well, that was a z-score of 2. We were 2 standard deviations above average when I start being late. So let's use the same logic and say, okay, well, if I'm average or faster, obviously I'm fine, right? So half of the time, 50% of the time, I'm average or better. So that'll be good. Let's look at what's slower than average but still not late. So with the Briley route, that was 2 standard deviations above average that I was still okay. It was at 2 standard deviations that I start being late. Well, our 68, 95, 99, 7 rule says within 2 standard deviations, we have 95% of the data. So that means on one side, remember we already factored in 50% of the time I'm faster than average and I'm fine. So we're just going to look at the above average but below standard deviation section of the distribution. Well, that's going to be 47.5, right? Half of 95. Well, a symmetric distribution means the part of that that's above average is 47.5. So 47.5% of the time, I'm going to be slower than average, but still not more than 2 standard deviations slower than average. So I'm going to be later than I normally am, than my average, but not actually late, because it's at 2 standard deviations that I start being late. So that means if I take the Briley route, 50% of the time I'm faster than average, I'm fine. 47.5% of the time I'm slower than average, but I'm still okay. So add those together, and 97.5% of the time I can expect to make it in time for class to start. That means what's left? 2.5% of the time. That's those days when you're more than 2 standard deviations above average travel time. That's when I'm late for class. 2.5% of the time when Briley gets really backed up with traffic, which doesn't happen much at all, but it's still possible, right? We live in a world of uncertainty. And that's where the power of the 68, 95, 99, 7 rule, we can actually pin probabilities down to help capture that uncertainty that we have in the world. So instead of just saying one route is more likely or less likely to have me be late, we can actually say by how much. We can quantify it. I expect to be late 16% of the time if I take the downtown route, because I'm on time 84% of the time. If I take the Briley route, then I'm going to be late 2.5% of the time. I'm going to be okay 97.5% of the time. So obviously, with these numbers, I prefer taking the Briley route because I really don't like being late for class, and I'm happy to see you guys. I wish I had that issue right now because I miss driving to Bowling Green and seeing all of your faces. But we play the hand we get dealt, right? So the 68, 95, 99, 7 rule helps us make sense of what hand we're being dealt and how to pin probabilities down when we're thinking about that.